Okay, welcome back everyone. So in the previous videos you've seen the algorithm of k-means clustering, which is one possible algorithm you can use in the clustering paradigm or the unsupervised paradigm of machine learning. We'll today look at another algorithm in the same spirit. It is called hierarchical clustering. I will briefly run through how this hierarchical clustering works. It's quite intuitive, and once I do that, we'll also talk about post doing k-means or hierarchical clustering. We obtain certain clusters. So we'll also look at what do these clusters mean, how do we interpret them, or we'll look at how to describe if if one element is a part of one cluster and if another element isn't, what are the most defining attributes that differentiates these two scenarios. Okay, so we'll start off with hierarchical clustering. Uh, I would like you to pause and think about how you would go about solving a jigsaw puzzle. Uh, okay, so the process is very similar to what you would do in hierarchical clustering. So initially you would probably try to identify two pieces that are quite similar to each other, and then you will combine them. Then perhaps you may find another piece that you would want to join to the same pair that you already made, or else you would want to you would have maybe found some other two pieces or three pieces which are similar to each other, and you would cluster them. And if you keep going on with this process, at the end you would have combined all of them into one single cluster, and that would be the solution to your puzzle. And now this process is very similar to what we do in hierarchical clustering, if not the same. So we'll illustrate this with an example. So now so we'll look at these 4 points over here, right? And now here I would like you to pause and tell me which of these points among these four are the closest to each other. So these are my four jigsaw pieces, if you will. I'll also mark the coordinates for you. So those would be, so this one is 5 on the x-axis and 5 on the y-axis. Then I have this point which is 5 on the x-axis and 6 on the y-axis. Yeah, then this one would be 8 on x, 6 on y, and this is 7 on x, 5 on y. You already seen how we calculate the Euclidean distance in the previous videos. Now given these 4 points, can you find the pair of points that are the closest to each other? I hope you've found that. The answer is 5 comma 5 and 5 comma 6, because these two are a distance of 1 unit apart, 1, whereas these ones, it should be by the Pythagorean formula, it should be from 7 to 8 there is a deviation of 1, so 1 squared, plus from 5 to 6 there is also a deviation of 1, which is 1 squared, so this is root 2, and these just visually, I mean this is 2 units apart, this is 3 units apart, so these two points are the closest. Now what we'll do is, as we saw in our jigsaw example, we will first put these together in one cluster. So I'll use yellow over here, and I will first connect these two, if you will, and make one cluster. Then what I can do is I can connect these two and then make a cluster, and then further this part would be my third cluster, but we'll come to that. So this kind of process, I'll now show you a chart which you can use to kind of record this or bookkeep whatever we are doing currently. So I'll start off with, I'll introduce that as well. So I'll have this axis, I'll call this distance, and here yes, so now we have 5 comma 5, 5 comma 5, then we have 5 comma 6, then we have 7 comma 5, 7 comma 5 and 8 comma 6. Now I have these 4 points. Now the distances between 5 and 5 and 5 and 6 were 1 1. So along this distance axis, perhaps this is 1, this is 2, and so on. And now since we kind of combined 5 5 and 5 6 while they were at a distance of 1 unit apart, we will draw these lines here. Yeah, so we have 5 5 and 5 6 connected at distance 1 apart. Then we also have 7 5 and 8 6, so that would be this point and this point here, and they were connected at a distance of square root 2 apart. So that is square root 2 is 1.414, so it's somewhere along here. So I'll draw a line for that as well. So that would be, yes. As you can see in the diagram, the distance on where they are being connected is also encoded. So we will see why this is useful right in a bit. And then thirdly, we combined these two clusters also together. This part, finding the distance, is a little, I will explain on further, but for now we will just consider this distance between these 2 points, and that would be 2, right? 5 to 7, yeah. So this is a 2 units apart, so they would connect over here. So I have this, right? So this was just on these particular points, but you also have points on the top, and we've sort of constructed some chart here. If we keep continuing this process of constructing this chart, this is the diagram that we will obtain. This. So here, as seen before, we had 5 5 and 5 6 connect at 1, then 7 5 and 7 5 and 8 6 connect at 1.414, which is over here. Then those two connect each other at 2. So that was the part which we drawed, and it so happens that the other points also start combining while we go through this process of solving while alluding to the jigsaw example. We see that 8 10 and 6 10 connect first, which is, we go back here, yeah. So this was 8 10 and this is 6 10. So these are closer to each other than these points, so these will connect to each other first, then this will join the cluster formed by these 2 points, and then finally they all join at around over here, right? So this diagram, the way we kind of bookkeep our jigsaw process or the hierarchical clustering process, is called a dendrogram. Dendrons being similar to the ones you have in nerves, where you have certain branches coming out from a certain center. So that would be here, and you have multiple branches coming out, and these are the point labels, and these are the distances where we actually combine these points to cluster them, if you will. Now all this is fine, but since this is a clustering exercise, now we will discuss how you can retrieve clusters from this particular diagram. So we do that by cutting the dendrogram. Let me in fact show you before coming here. Now suppose I'll cut my dendrogram. If I cut my dendrogram over here, right? Yeah, it should have been a straight line, but assume it is for now. You can see that if I cut this particular connection is gone, and so I have two disjoint trees kind of structure here, and these exactly form a cluster. So I am saying 5 5 5 6 7 5 and 8 6 is in one cluster, and 5 12 6 10 and 8 10 is in a separate cluster. Whereas if I choose to cut this at a different point, say yeah, somewhere here, right, then I have this one, which is a single one, and then we have two here. So if I choose to cut it there, I have 4 clusters. One would have 5 5 5 6, the other one is 7 5 8 6, the third one is just 5 12, and the fourth one is 8 10. We also visualize these on the next slide. Yeah, so this is the exact same data set. So now yeah, so first if we, since we are cutting, now note that if you are cutting it at the bottommost part, you just end up with every single point in its own particular cluster. So here we have how much, 1 2 3 4 5 6 7 clusters, so that's why these are also colored that way. Now but if we move this a little up, so for example if we move it over here, you see that all these points are still in their own clusters, but we've clustered 5 5 and 5 6 together, which is what, if you recall, when we constructed this part of the dendrogram, we did exactly did, right. So cutting this dendrogram that way yields us this particular cluster. If we move it a little further up, so at around 1.5, which was greater than root 2, which was 1.414, we should get 2 clusters, and you can see that as well, right. So 5 and 5 6 over here, sorry, yeah, 5 5 5 6 here, 7 5 8 6 over here, and the rest are just singleton clusters. Now the third one, we can move it further up, and you get these two points clustered together. And then if we move it a little more up, as you can guess, we will have these 3 points, sorry this one, yeah, since this is lower than this junction, so we will have these 4 points clustered together before that happens. So we have these 4 and then these 3, and then finally we will combine everything to get our entire point collection in one particular cluster. Now we as domain experts in various applications, we can choose where to cut our dendrogram, we can choose how many number of clusters we want, and then we can investigate why such clusters even happen. So we will do that shortly using some data sets, but now we will move further in this, right. So we have, yeah, so we'll require some terms. So the clustering I just showed you is called the agglomerative approach to clustering. Agglomerative is just a word that says bottom to top. So you start off with all your points in their own individual clusters, as we saw in the previous animation. Yeah, so if I go here, all of my points are in their own individual clusters. Then what we do is progressively we start combining them, like how we do in a jigsaw puzzle, and then we get the agglomerative approach. There are also other approaches. For example, there is a divisive clustering approach where you have all of them in a single cluster, then you find the best partition between these two, and you keep going until you have all your points separately. That's outside the scope of this lecture, but that is also another approach to hierarchical clustering. But what we just showed is called the agglomerative clustering approach, and we also used something called the single linkage to actually combine clusters together. Now this is what single linkage is. For example, I have two existing clusters, and I want to decide on whether I want to combine them or not. Then I will look at, so I will consider every element inside cluster 1, I will consider every element inside cluster 2, I will take all their distances. So I have CH, CF, CG, EH, EF, EG. So I have total of 1 2 3 4 5, and then 1 2 3, I have 5 times 3, 15 distances which are candidates, and then I will choose the least of them and then combine with all my other candidates also, and see if this is minimum, I will combine cluster 1 and cluster 2. In fact, this particular red distance would be the one that we used to sort of combine here. For example, if we go to the penultimate step here, yeah, so if you go to the penultimate step here, we have 3 points and here we have 4 points. Now we are using single linkage here. Now if we see that, so we'll take all the distances between these points and these points. So we have this as one particular distance, this as a distance, but if we can just eye it out and see that these are the closest to each other. So this is I'll mark it as well. So this was 8, 6, and this is 8, 10. So we see that yeah, the distance is 4 because from 6 to 10 we have 4, it's 4 units apart, and therefore these combine over here at 4 along the y axis. So that is that, and that is how so this is the single linkage term. Whereas there is another metric that we can use to combine these clusters. There are various metrics, and that is called complete linkage, where instead of using a distance that's the smallest between these two clusters, we will consider the distance that's the farthest between these two clusters. So in this example, we see that the distance between D and H is the farthest among all the possible 15 distances that you can obtain from these two clusters. So if we had to use that over here, then that would have been probably the distance between this and this, or this and this. We'll have to calculate and see, but one of those. So you can see your dendrogram also changing. The clustering, ordering, all those will change based on the linkage metric you choose. But yes, that is what we have. And thirdly, for all these linkages to work, right? So here we saw we required all the 15 distances, but when we start off, we require all the distances between all points. So we need all pairwise distances of points, and we can use a matrix to encode this. So suppose, so this is called a distance matrix. Suppose if I have a matrix D, then its ijth entry would just be the distance between points I and j. So once we have these distances, then linkage can do its job. So it can then decide on the minimum distance, maximum distance given the clusters. It can take care of the computations for us. So right, so that was a primer on hierarchical clustering. We'll now also demonstrate all of these in orange.